Okay, so for right linear grammars, the set of languages it accepts are regular languages, and there's a collection of automata that is corresponding to those class of languages, that is either DFAs or NFAs. Now, context-free grammars, the languages that they can generate are the context-free languages, and they too have corresponding automata. In this case, the automata is called a pushdown automata. Informally, a pushdown automata is like a finite automata, either deterministic or non-deterministic. That's also called a stack. So a DFA or an NFA have finite memory, and their memory is encoded in what state you're in, whereas a PDA is infinite memory. It's also got a stack. And a stack is this great big infinite pile of memory that you can either push things on top of or pop things off, but you can only ever see the very top of the stack. Okay? So that's like intuitively the definition. Let's look formally at the definition. So formally, a deterministic pushdown automata is a 7-tuple, Q, Q naught, F, sigma, gamma, Z, delta. Q is a set of states. Q naught and Q is the initial state. F as a subset of Q is a set of all final states. Sigma is the alphabet, which is the set of all symbols that the input can be made from. Gamma is a set of all stack symbols, so the set of all symbols that can live on the stack. Z, which is an element of gamma, is the initial stack symbol. That will mark where the bottom of the stack is, so we know where the stack when the stack is empty. And delta is a partial transition function. So that when I say partial transition function, partial means the function may not be defined for some inputs. So if the function is not defined for some inputs and you try and evaluate it for an input, it'll be undefined and it will immediately be rejected. Okay, so what's a partial transition function? It takes in three things. It takes in the current state, takes in either the current input symbol or epsilon, so you may or may not have to actually read the input, and takes in the top of the stack gamma, transitions to a new state Q, and replaces the whatever was on the top of the stack with a new top of the stack. That can actually be a string, so it's actually gamma star. Okay? We note that if Q delta epsilon S is defined, that is, from state Q I can read nothing and go somewhere, then for all other input symbols, QAS, delta of QAS must be undefined. The reason is because then I could get to choose whether or not to read input or not. And being able to choose basically introduces non-determinism, which is not what we want for a deterministic pushdown automata. Now, if from state delta, reading an input token A, and popping S off the stack, if that transitions to state Q prime and pushing sigma on the stack, we denote that as this notation here with a fraction, and in the little flowchart diagram for the automata, that translates in this notation here. So from Q, read A from the input, pop S off the stack, push sigma back onto the stack. Okay? And final states are denoted with an underline. Okay? Now, when we're doing a transition that involves an epsilon input, that consumes no input and can always be performed because any string starts with epsilon. But when I have delta QAS, I am going to actually gobble up some input, so I'm going to consume the A, and I can only perform that input if the input was prefixed with A. So that's just the definition of a pushdown automata. And we'll go through some examples of how to create them for a language and how to convert context-free languages pushdown automata. Because if a pushdown automata really is the language, that really is the automata corresponding to context-free languages, then we should be able to freely convert between one and the other.